Okay, so let's talk through sets. I assume you've seen sets before, so I'm going to go fairly rapidly through this. Okay, a set is a collection of elements or members. You know the representation of a set. Usually you can make a circle, and then the elements are dots in the circle. Okay. You can specify a set by listing the elements or by determining a property. Okay, so here's two examples. So here, for instance, you can write a set of positive even integers in this way or as a property. Okay. All right, so here's some examples and so on. Okay. You can have sets of sets or in sets of sets of sets. So there's a lot of, in the field of logic, there's a lot of taking sets of sets and the notion of cardinality. How many sets of sets are there? Infinite sets. Various very interesting things about that. But we're not really going to go into that. We're mostly going to be dealing with finite sets. Here's a little contradiction. I won't go into this, but this is kind of for cultural enrichment. Okay. One point is that usually when we're talking about sets, you usually specify one universal set that all of your sets are contained in, and this eliminates any possibility of confusion. So, for instance, if we're talking about sets of real numbers like integers or rational numbers or negative numbers, we first specify that we're dealing in the universal set of real numbers, and then we can talk about subsets of real numbers. Here are important symbols that we use for various types of numbers. The natural numbers starting with 1. In some books, natural numbers start with 0. The integers, the rational numbers, the real numbers, the complex numbers. So these are the standard symbols. Okay. Subset, here's the notation for subset. You can verify that this string of subsets is true. The natural numbers is contained in the integers, is contained in the rational numbers, is contained in the reals, and so on. Okay, so there's a difference between proper subset and general subset. Technically, a set is a subset of itself. For instance, if I have the set of integers, then the set of integers is a subset of the set of integers. But we say it's not a proper subset. Proper subset has to have some elements that are not in the subset. So proper subset can include the entire set. Some authors use different symbols for subset and proper subset, but we're just going to use this symbol for subset, and we'll tell you when we're talking about a proper subset. Okay. The empty set has no elements in it. The empty set is a subset of every set. So usually you're interested in non-empty proper subsets. Okay. Now this is an algebra course, so of course we're going to talk about algebraic operations. You can do operations on sets. Okay. Two common operations are union and intersection. Union means take all elements that are in one or the other. The intersection means take all elements that are in both. You can do multiple intersections, multiple unions. Remember, you can draw those Venn diagrams. If you have 3 sets, tablet here. If you have 3 sets, that represents one set, that represents another set, that represents another set. Then the intersection of all 3 would be this thing in the middle here, and the union of all 3 would be all this, the entire shaded area enclosed by at least one circle. Right. And we can prove properties of these operations. So here's some various exercises with unions and so on. Okay. Some more exercises with unions and intersections. Okay. Two sets that have no elements in common are said to be disjoint. The complement of a set, so the picture for complement you can draw like this. If your universal set is the big rectangle containing everything, and A is a set in U, then A complement is going to be everything outside. The set difference is whatever is in A that's not in B. You can draw a picture of that. If you have A here and B here, if this is A and this is B, then A not B, you say A not B, the difference is everything in A that's not in B. So it's this part here. It's A, and take out the intersection between A and B. Okay, more exercises with sets. More exercises with sets. Okay, so let's consider properties of set operations. Okay, let's see. So here, for instance, we're talking about the operation of intersection, and the relation of less than. And here's the operation of union, the relation of, I'm sorry, not less than, but contained in. Okay, and the way to prove these things is by element, because the definition of intersection and union is element by element. So see how this works with the one on the left. So we're going to show that every element in A intersect B is also in A. So if X is in A intersect B by supposition, then X is in A and X is in B, that's the definition. And that means X is in A, that's by logic rules. Now, to be complete, we should go through the logic rules, but we're just going to deal with logic informally, that if something is true and something else is true, then either one is true. So we're just going to use logic as the defining reason for making conclusions such as this. But the point is, you go from the set argument to a logical argument involving the elements. Okay, so here's some various other operations and similar element by element proofs. Okay. All right, I'm going through this quickly because, as I said, I think that people should have a background in sets. Let's do one of these in particular. Suppose we want to prove this is proving the associative law for union. So let's go through this one in detail. So, as I said, to prove the associative law, to prove things about sets, you want to reduce it to an element by element argument. If you want to show two sets are equal, then you want to show every element in one is also in the other. Okay, so let's characterize the elements in this set. The elements in this set are A, union, the elements X, such that X is in B or X is in C. Okay. So if we want to use, again, the element by element characterization of the union of A with this set, we can characterize in terms of its elements this way. X is in A, or X is in B, or X is in C. So actually, we're kind of using the associativity of logical statements, the associativity of or. Okay. Now, by the definition of union, the union of these two sets, X is in A or X is in B, with C, is defined as this set also. So, really, you can think about this proof of saying that A union B union C reduces to this set here, this logical set here. And A union B first, result union C, also reduces logically to this set. So both reduce logically to this set. This is the logical expression of both sets. Okay? So you can prove these other distributive and associative properties in a similar way. And so I invite you, if you need more practice, to go through this element by element argument. It has a similar flavor to what we just showed. Okay. All right, so here's some more. So I'll give you some practice in proving these things. Okay. All right, again, let's look through this proof here. This is one of De Morgan's laws. These are very important because you have to talk, if you want to simplify expressions that involve set complements, you can simplify everything down to primitive operations operating on the individual complements themselves. All right, so let's look at this first one. One way to do this is to show that every element in this set is also in this set, and vice versa. That every element in this set, A prime intersect B prime, is also an A union B, the result prime. So that's the strategy that's used here. You show that each set is a subset of the other. Right, so the first way would be to show that every element of A union B, complement of that, is contained in A complement intersect B complement. So take an element in A union B complement. By definition, it's not in A union B. So it's neither in A nor in B. Okay, because A union B means it's in A or B. So if it's not in A or B, it's neither in A nor B. Okay, again, we're using logic here. By the definition of complement, X is in A complement because it's not in A, and X is in B complement because it's not in B. Therefore, X is in A complement intersect B complement because it's in both. Okay. So what have we shown? We've shown that we start out with an element in A union B complement, and we show that it's in A complement and in B complement, therefore in A complement intersect B complement. That gives us that every element of A union B complement is in A complement intersect B complement. To show the reverse, suppose that X is in A complement intersect B complement. That means that X is in A complement and X is in B complement. So X is not in A and X is not in B. Okay, so that means that X is not in A union B because it's not in A or B. Okay, so X is in A union B complement. Okay, so these other propositions you'll prove similarly. Okay, once you've built up these primitive rules, just like in complex numbers when we did complex conjugates, once you've built up primitive operations and primitive identities, you can prove statements about set operations without going back to element by element. And this is really the goal, because that's what abstract algebra is, being able to work with operations that have been defined and have properties and use those properties to prove important statements. So follow this along. This says that A not B, A set difference B, intersect B set difference A is empty. Now it does help sometimes to draw set diagrams to see where you're going here. So if you have A and B, like this, what is A not B? Well, A not B is this part here. B not A is this part here. Okay, so that is A not B is A without the intersection of A intersect B. B not A is B without the intersection of A and B. So they don't have any intersection. Okay. So you can kind of show this by a picture, but that's not really a proof. Let's do a proof using the algebraic properties of set complement. Okay, so let's start out with this. Let's do algebraic manipulations. Now the definition, usually you first go to definitions. Definition of A set complement B is A intersect B complement. The definition of B set complement A is B intersect A complement. Okay, now because we have associativity of intersection, we can change the order of parentheses. Also, we can change the order of intersection. For instance, we can move this A complement, and we can move this A complement after the A. So we're actually using two parts of this proposition. We're both changing the order of parentheses. We're removing the parentheses because since it's associative, it doesn't matter which order you do the operations in. And we're changing the, order in which we actually write the sets. That's commutative property. Okay, we basically commuted this A prime with this B, and then once the A prime is here, then we commute it with the B prime. Okay, so associative and commutative allows us to rearrange arbitrarily. Okay, then you can group this part and group this part, and that gives us empty set intersect empty set. All right, there are some details that are not included in this write-up, so hopefully you can see how that's working there. And the empty set intersect the empty set is the empty set. Okay, so you should be able to do the same thing with this. Remember, you take this definition and you'll use some of these set identities. Okay, you use, in this case, I think you use the distributive law or something like that. Maybe not distributive law, but you'll use something. Okay, so here's a lot of identities to practice on. Okay, so here's a question: do subsets of a set form a group? Now we have operations on sets. Perhaps these operations give us a group. So in this section we investigate this question. Now remember that the properties that a group has to have. The group operation has to have the property of closure. In this case, for instance, if the sets with intersection is a group, that would mean that the intersection of two sets would have to be a set. The set has a unique identity, unique inverse, associative property. Okay. All right, so let's see. Okay, so as I said, here we investigate this question: is the set of subsets is the set of subsets of a given set a group? All right, so you just work through these exercises and see if all of these properties hold. All right, so I'm just going to skip here. All right, so I think that's all I'm going to say about sets.